Okay, let's solve some problems. This is Dr. Smith. You probably know me better as the TJ HSST Winter 2011 Dancing with the Faculty champion, but today, instead of showing off my massively amazing dance moves, I'm going to solve some problems. So, let's look at this problem number 1 here from the Work and Energy 2 assignment, where we've got this block lying on a horizontal frictionless surface attached to the free end of the spring. I'm going to go ahead and copy this image. There's a spring constant of 55 newtons per meter. Initially, the spring is at its relaxed length, and the block is stationary at position x equals 0. Then an applied force with constant magnitude 3.1 newtons pulls the block in the positive direction of the x-axis, stretching until the block stops. Assume the stopping point is reached. What is the position of the block is A. Now, I don't know why they need to explicitly tell us to assume the stopping point is reached, but okay, whatever. You know, they just like to tell us that. So this is the situation, and we have this applied force. Oops, sorry about that. Let's see. There we go. We have this applied force F. I'm going to call this F sub A for applied force. And the spring force, once this gets stretched, there's going to be a spring force pulling backwards. The block is going to move in the positive x direction. Okay, so FA is a constant, and they told us what it was, I forget, but anyway, Fs is going to equal, if you recall, the spring constant times the displacement of the block, so times the amount the string is extended, and it's going to try to pull back towards the the rest point. Okay, so what's going to happen here is that as this thing starts moving to the right, it starts at rest, it starts with the spring at its rest position, and it starts with the the block at rest, and it's being pushed to the right by this FA. So what's going to happen now? Just think about this for a minute. What's going to happen is you're going to have, in fact, I'm going to draw a plot of force versus let's do force versus position. So starting from a position of 0, we have two forces acting out. One is going to be this force Fa, which is, I won't draw an arrow there, but whatever. Okay, which is a constant force, right? So it stays the same as the block moves to the right. As x increases, this applied force remains constant. The other force is going to be this force due to the spring, which is going to start, oh, now I've got the eraser still, which is going to start at 0. This is going to be this equation here for Fs, and it's going to increase linearly as x increases. So this line here is going to be Fs, which is going to be negative k times x. We know that. Okay, so this red line represents our applied force. This red line represents our spring force as we move to the right. So what we can do is we can find the work done by each force by looking at the area under these curves. So, for example, we go out to some point, we'll call this point x here. This is where the block is extended out to. And let's say we're going to let orange be the work done by the applied force, and that's going to be the area of this thing here, right up to the blue line. Okay, so all this area under the applied force is the work done by the applied force. So, work done by the applied force. And this is just a rectangle, right? So it's going to be Fa, which is the magnitude of the applied force, times x, which is the distance over which this applied force acts. It's constant. Easy. Okay. Now, what's the work done by the spring force? Well, that increases as we go to the right too. So, but yeah, because the force is changing, it's not this rectangular area. This area here is the area the work done by the spring force, and it is more of a triangle. So right here at this point x, we just do this. Spring force equals negative kx, but the work done is the area of this triangle. So let's say the work done by the spring is going to be the area of this triangle, which is 1/2 base times height squared. Sorry, 1/2 base times height. So the base of this triangle goes from 0 to x. So that's just times x. And then the height is negative kx times negative kx. Okay, so the total work done by the spring is negative 1/2 kx squared. The work done by the applied force is just Fa times x. So our first problem is to find how far this thing goes before the block stops. Now, you can imagine what happens here is as you're moving to the right, the block is speeding up. You know, initially it's speeding up due to the applied force because the spring force is very small. The applied force is constant, but the spring force starts out very small. And then you get to a point where the magnitude of the spring force is the same as the magnitude of the applied force, but they're pulling in opposite directions because the spring is pulling back this way. So it stops accelerating. So if you looked at, like, you know, its velocity versus its position, you know, then you'd have something looking like, just intuitively, velocity versus position, you'd have something looking like starting like this and increasing pretty fast, and then around here this would taper off and it would stop increasing in speed because this is the point where these two are equal. This height and this height are equal, so it's no longer speeding up. And then it starts slowing down because now the spring force is stronger than the applied force, and it starts slowing down, and then it goes like that. And what's going to happen eventually, actually, is it's going to go negative. But what we're interested in is this point here, where it comes to a stop. How do we find that? Okay, so this is a unit about energy. So what we want to find is some way to express this in terms of energy. At the end, the point where this block stops, that's where the block's velocity is 0, and that means the block's kinetic energy, which I represent as E sub k. Some people use a capital K. I think Mr. Hannum does that. That's fine. It's 1/2 mass of the block times v squared, which is going to equal 0. So what we know is at this point, initially where its velocity is 0, kinetic energy is 0, right there. And we also know that kinetic energy is 0 here at the end. So now let's look at what, you know, how much work is done by these forces and how that affects the kinetic energy. For a single object, we can use the single object version of the work energy theorem, which is that work equals change in kinetic energy. For a single object, we're not dealing with potential energy or anything like that. We're just doing the work done by the spring. Then what we want to do is say that the total work done on this block is going to be the change in kinetic energy. So it starts at 0. We want when it comes back to 0, which means the total change of kinetic energy over this whole period is 0. Starts with 0 kinetic energy, ends with 0, so the change is 0. So we want to find a spot where the total work done is 0. Well, the work done there is the work done by the applied force plus the work done by the spring force. We want that to equal 0. Okay? So what that means is we solve an equation that looks like this. WA plus WS is 0. Well, WA is this magnitude of this applied force times x. And work done by the spring is negative 1/2 kx squared, which equals 0. And the solution to that, well, one solution is x equals 0, and another solution is x equals, let's see, it looks like it's going to be 2, I want to make sure I get this right, 2f over k. Is that right? I think that's right. K times, yes, that's right. So it's going to come, so this, we got two positions where kinetic energy is 0. One is at the beginning, where x equals 0, right? That one's sort of the obvious, redundant one. The second one is at this point, x equals 2f over k. So this point here, right there is where it stops. X equals 2f over k. So I just need to plug that into my calculator and see if that comes out right. Okay, so the applied force is 3.1 newtons, 2 times 3.1 newtons, divided by the constant being 55 newtons per meter. So 0.113 meters should be my answer. Let's keep our fingers crossed and hope that the WebAssign gods smile on us, and they do. I'm going to show you another slightly different way to do this, and that is going to be in a separate video because this one's about 10 minutes long already. So Back in a second.